everyone, and welcome to Physical Geography 100 Lecture Podcast Series. I am your instructor, Brian Krause, and today we're going to be in Chapter 4, where we will be discussing insolation and temperature. In this mini lecture, like all mini lectures, I don't cover all topics or ideas presented in the text. Rather, my aim is to highlight a few key ideas and discuss them in a bit more detail. In this lecture podcast, I've included some concept checks in the form of non-graded quizzes at the end. When you get to the quiz slides, right-click the mouse and select Pause, which will pause the narrated PowerPoint. This will allow you time to answer the question. Once you have answered the question, right-click the mouse and select Resume, which will restart the PowerPoint. The following slide will provide the correct answer and explanation. If you're watching this video, you don't need to right-click the mouse. Simply use the controls at the bottom of the video to navigate. On that note, let's jump into the material. So matter and energy, essentially everything in the universe is made up of two things, matter and energy. Matter is the stuff of the universe, the solids, the liquids, and gases. Matter has a mass and it has a volume. Energy, on the other hand, is the ability to do work. So this stuff should start sounding familiar from some of your chemistry classes, maybe in college or in high school. And so when work is done, it's manifested in two variety of ways. Matter can be pushed, pulled, or lifted over distance when energy is applied. In other words, work is done on matter implies a change of position or movement. While there are many forms of energy, we will look more closely at two, potential energy and kinetic energy throughout this semester. Potential energy is the energy of position. For example, a block of rock attached to a high cliff face has substantial potential energy due to its position above the ground. When it breaks away from this cliff and falls to the surface, potential energy is converted to kinetic energy, which is energy of motion. Temperature and heat are also important concepts to understand, and temperature is a measure of the average kinetic energy level of a substance. In other words, it's the degree of hotness or coldness. Heat refers to energy that transfers from one object or substance to another because there is a difference in temperature between the two. Heat is transferred in three ways: induction, convection, and advection. And we'll look at these in more detail in the coming slides. Solar energy. So this is important in the coming up slides as well as kind of other chapters. So this is an important concept that you should understand. The sun is the only significant source of energy for the Earth's atmosphere. The sun gives off energy in the form of electromagnetic radiation, or just radiant energy. And the electromagnetic radiation travels through space in the form of waves, which is illustrated here in these two images. The typical electromagnetic radiation depends on the wavelength, and that's the distance between successive crests. And we can see this in the upper left diagram, where we can see the wavelengths in various widths. So the greater the distance between the wave crests, the longer the wavelength. Collectively, electromagnetic radiation of all wavelengths comprise the electromagnetic spectrum, which is the bottom image in this slide. So solar radiation is almost completely in the form of visible light, ultraviolet light, and shortwave infrared radiation, which as a group is referred to as shortwave radiation. This is what I said, is solar radiation that comes from the sun. Radiation emitted by the Earth, or terrestrial radiation, is entirely in the thermal infrared portion of the spectrum and is referred to as long wave radiation. So that is an important concept there, that solar radiation is shortwave and radiation emitted from the Earth, or terrestrial radiation, is in the form of long wave radiation. So here we're going to look at heating and cooling processes of the atmosphere. So what happens to radiation as it passes through the atmosphere? Before we get into this, let's define what radiation is. As your text states, radiation is the process by which electromagnetic energy is transmitted from an object. While all objects emit energy, hotter bodies emit more energy than cooler objects. So for example, the sun is much hotter than the Earth, so it emits 2 billion times more energy than Earth. So when radiation such as from the sun passes through the atmosphere, it can be absorbed, reflected, scattered, or transmitted. So let's take a look at that, what happens in each one of these processes. So absorption. When electromagnetic waves strike an object, that object may absorb that energy. As the electromagnetic waves strike the object, the molecules become excited. That is to say, they begin to vibrate, which in turn increases the kinetic energy of the absorbing material and makes that material warmer. Reflection is the ability of an object to repel electromagnetic waves without altering either the object or the wave. If a material is a good absorber of this electromagnetic wave, it cannot be a good reflector since it's absorbing it and not reflecting it. The proportion of light reflected from a surface is referred to as albedo. And albedo values range from 0 of no reflection to 1 for complete reflection of sunlight striking the surface. An albedo can be expressed as a percentage, so you have the albedo times 100 to create a percentage. So for instance, grass has an albedo of 0.23, which means that the incoming solar radiation that strikes the grass, 23% of it is reflected away. On the other hand, highly reflective surfaces like this fresh snow have an albedo of upwards of 87% of the sunlight is reflected away. It's kind of a good example of when you're skiing. Have you ever skied and you get like the sunburn underneath your chin or under the bottom of your nose? Well, that's from the sun reflecting off the snow and back up to you. Scattering is the deflection of the electromagnetic waves. When the electromagnetic waves are deflected, their direction is altered, but the wavelength is not. This deflected electromagnetic waves may be sent back to space or strike the Earth as diffused radiation. Generally, shorter wavelengths are more readily scattered than long ones in the atmosphere. So you might ask, so why is the sky blue on a clear, cloudless day? This is because of Rayleigh scattering, where molecules in the air scatter the shorter wavelengths of visible light, which are the blue and violet. At sunset, for example, we see red and orange because the blue wavelengths have been scattered away, leaving only the long wave lights, such as the red and orange. Finally, transmission is the process whereby electromagnetic waves pass completely through a medium. Different materials have varying levels of transmissibility. For example, a rock is very poor. You know, that's wavelength, that's electromagnetic. It's not going to penetrate a rock very deeply. But water is highly transmittable. Transmissibility is also very greatly depending on the wavelength of transmission. Ever wonder why the inside of a car heats up so hot on a warm day? It's because shorter wavelength radiation easily passes through your car window and is absorbed by the upholstery and is heated up. The long wave radiation emitted from the now heated upholstery can't easily transmit out through the windows, which causes the car to warm up and will reach temperatures greater than the outside. So this is kind of an example of the greenhouse effect that we'll be talking about. So this is why you don't want to leave your kids and dogs and grandparents in the car with the windows rolled up on a hot day. So the greenhouse effect is the warming of the air due to an atmospheric absorption of long-wave energy emitted by the Earth's surface. That is to say that short-wave radiation of the sun is more readily transmitted through the atmosphere, but long-wave radiation from the Earth is not. So these long waves are absorbed in the atmosphere by greenhouse gases, which water vapor and carbon dioxide are the two most important gases, and re-radiated back the energy as heat to the Earth, causing the warming, which we call greenhouse effect. And we will be talking more, and you'll be debating more about the greenhouse effect and global warming later on in this. Recall from an earlier slide that heat refers to energy that transfers from one object or substance to another because of a difference in temperature. So let's look at 3 different mechanisms for heat transfer: conduction, convection, and advection. Conduction is the transfer of heat between substances that are in direct contact with each other. Conduction comes about through molecular collision. So as molecules become more agitated, as the heat is added, they collide against cooler, calmer molecules, transferring this kinetic energy. Second, convection. Convection implies a vertical transfer of heat, like that which occurs in a heated pot of water. So as the water warms, it circulates to the surface. The same is true for air. When air is heated by the Earth's surface, it too circulates upward. I'll let you kind of think about this, but where do you think convection occurs the most on a kind of a global scale? You can certainly see convection on a hot summer day here in Boise, and if you look over the mountains, kind of where Bogus is, that mountain range there, and you see these huge, huge billowing clouds. Those clouds are a result of convection. Advection is the transfer of heat in the horizontal, so north, south, east, west kind of direction. In meteorology, the wind transports heat by advection. So I've included three illustrations here, which you should be able to identify as either conduction, convection, or advection, and why it is so. Adiabatic cooling and warming is a very important concept that we will touch on here, but we will be talking in greater detail about it in coming chapters. So whenever air ascends or descends, its temperature changes. So in adiabatic cooling, as this parcel of air rises, and in this diagram, a balloon is representing a parcel of air, this air pressure exerted on the balloon decreases with increasing altitude. Remember from earlier lectures, as you rise in elevation, there is less and less pressure there. There's less molecules to be pressing down on you, so if there's less pressure, this balloon, or this parcel of air, has the ability to expand. And because there is less pressure exerted on the balloon, the molecules can spread further apart because the balloon, or this air parcel, is expanding, which in turn causes the molecules to collide less frequently, since they're not in such a close contact, which reduces the kinetic energy, which causes a decrease in temperature. So if these molecules are moving around really, really slow, not touching other molecules, well, they're going to have less kinetic energy compared to if the molecules are going berserk and bouncing off each other and bouncing off the walls. That's producing lots of kinetic energy, which produces greater temperatures. In adiabatic warming, as the air parcel, again described as this balloon, becomes under increasing pressure as it descends, which causes the molecules to be in close contact because this balloon is decreasing in size. They collide more frequently, resulting in more kinetic energy, and therefore warms the parcel of air. So this understanding of as air parcels rise, they cool, and as an air parcel descends, it warms because of this adiabatic process is important to. So the next is Earth's energy balance. And Earth's energy balance, or radiation balance, is an accounting of the incoming and outgoing components of radiation. So these components are balanced over long periods of time and over the Earth as a whole. So if they weren't in balance, the Earth would be continually either cooling or warming. In other words, if the Earth and the Earth's atmosphere retains more solar energy than it radiates back to space, the Earth will warm. If the Earth and the Earth system radiates more energy to space than it receives from the sun, the Earth will cool. So the radiation balance of the Earth system is depicted in this figure, where short-wave radiation is colored in yellow, and long-wave radiation is indicated in red. In this figure, 100 units of radiation of energy is used to represent the average total insolation received at the outer edge of the atmosphere, and trace being its dispersal down to the surface of the Earth. It is not my aim to walk you through this incoming and outgoing radiation budget, but for you to get a general understanding of what is occurring. Furthermore, it is not important for you to know these various units, but to understand that there is a general balance of incoming and outgoing radiation. One thing you should think about is how do greenhouse gases alter this energy balance? Also, is the Earth's atmosphere primarily heated from above or below, and why? Recall the vertical structure of the atmosphere lecture to help you answer this. As one might suspect, the Earth is not evenly heated. Needs to be some kind of mechanism to distribute the heat from regions of surplus to regions of deficit. And we'll look at these in the remaining slides. So the first two causes in variation in the Earth's heating that we'll look at are latitude and seasons. Because the Earth is a sphere, and not all areas on the Earth are going to receive the same amount of insolation at a given time. And this should sound familiar from earlier lectures that we've discussed. This is illustrated here on this slide. When the sun's rays hit the Earth at an angle of 90 degrees, the sunlight spreads out over the smallest possible area. And you can see this in the upper left, and it's upper left figure here, and it's also shown in the green, where that little box of that amount of energy is confined to that little area. But when the Earth hits, or when the rays hit the Earth at an acute angle, the angle that measures less than 90 degrees, the same amount of insolation spreads out over a larger area. And because the same amount of energy covers a larger area, each part of that area gets less energy. So the more acute the angle of the sun's rays hitting the Earth's surface, the less thermal energy a particular place gets. So you can see 90 degrees, the green box is very small, lots of intense energy, where if you go up to 10 degrees, the amount of surface covered by the insolation is significantly more, so that same amount of energy has to be spread out over a much larger area, meaning that it's not going to be as much energy. Next, atmospheric clouds, particulate matter, and gas molecules in the atmosphere cause a reduction in the intensity of energy received at the Earth's surface due to absorption, reflection, or scattering of insolation that we just discussed. So there are two key factors that affect atmospheric obstruction: the amount of atmosphere the radiation has to pass through and the transparency. So for example, a ray at 90 degrees has to pass through significantly less atmosphere than a ray at 10 degrees. And this can be shown here on the lower right image here, where it's showing that the radiation coming in at 90 degrees, the bottom squiggly line, and shows you how much insulation or how much it has to pass through the atmosphere compared to up towards the North Pole. It has to go through much more atmosphere, so there's much more chance for absorption and scattering and reflection and so forth. Therefore, there's going to be less atmospheric obstruction occurring at 90 degrees than at 10 degrees. And this can be seen, as I said, just in this image here on the lower right. And transparency most often refers to cloud cover. As cloud cover increases, less radiation reaches the Earth's surface. So day length is also an important factor in heating. So the annual amount of incoming solar energy varies considerably from tropical latitudes to polar latitudes. At mid and high latitudes, it also varies considerably from season to season. And this can be seen in this figure here. Notice at the equator that the energy is relatively constant year-round. And we can tell that by the line kind of doesn't have these highs and lows. It's relatively flat. And this is due to 12 hours of daylight year-round. Next, let's look at the 60 degrees north in January. In the northern hemisphere, the Earth is tilted away from the sun and is outside of the circle of illumination and receives little daylight. Therefore, the amount of insolation or energy that reaches the surface is very little. However, in June, which is summer in the northern hemisphere, and the Earth is tilted towards the sun at this time of year, the day length is greatly increased, so the amount of energy received at the Earth's surface increases, and this can be seen for the 60 degrees north latitude during June and July, where it's at its peak. And the reverse of this is seen for 60 degrees south, where their summer is our winter and vice versa. So generally speaking, highest values of surface insolation occur in tropical latitudes. Within this zone, there are localized maximums over the tropical oceans and deserts where the atmosphere has virtually no cloud development for most of the year. Insolation quantities at the equator over land during the solstice are approximately the same as values found at the mid-latitudes during their summer times. And outside the tropics, annual receipts of kind of solar radiation generally decrease with increasing latitude. And minimum values occur at the poles, and this pattern is primarily a result of the Earth-Sun geometric relationship and its effects on the duration and intensity of solar radiation received. This figure illustrates the annual values of net shortwave and net longwave radiation from the South Pole to the North Pole. So on closer examination of this graph, one notes that the lines representing incoming and outgoing radiation do not have the same values. For example, from 0 to 30 degrees latitude north and south, incoming solar radiation exceeds outgoing terrestrial radiation and a surplus of energy exists. The reverse holds true from 30 to 90 degrees latitude north and south, and these regions have a deficit of energy. Surplus energy at low latitudes and a deficit at high latitudes results in the energy transfer from the equator to the poles. And this is the main transportation of energy and causes atmospheric and ocean circulation. If there were no energy transfer, the poles would be about 25 degrees Celsius cooler, and the equator would be about 14 degrees Celsius warmer. So this energy transfer mechanism or transport is very important. So as we've been discussing, the atmosphere is largely warmed by heat re-radiating and transferred from the Earth's surface. Because of this, it is interesting and important to see how different types of surfaces react to solar energy. We'll briefly look at this land and water contrast, since these are the most significant. In general, land heats and cools faster than water does. Why do you think this is? Well, there's 3 or 4 key reasons: specific heat, transmission, mobility, and evaporative cooling. So please take a closer look at these 4 reasons in your text, and I'll not cover them here, but they are important for you to know. So the interesting question here is, how do these 4 things kind of affect annual temperature change for 2 different places with same latitude? And this is illustrated in the lower right figure. You should be able to explain why San Diego has a relatively constant temperature while Dallas has a more extreme variations. And finally, why the average annual temperature is roughly the same for each place. So you should be able to understand this concept of this. As our text mentions, if there were no mechanism for moving heat poleward in both hemispheres, the tropics would become progressively warmer until the amount of heat energy absorbed equaled the amount of heat energy radiated from the Earth's surface, and the high latitudes would become progressively colder. So as you're aware, this does not occur because there are 2 mechanisms of heat transfer from the tropics to the poles: atmospheric circulation and ocean circulation. We'll hold off on discussing atmospheric circulation until chapter 5, but we will discuss ocean circulation here in the next slide. So an ocean current can be defined as a horizontal movement of seawater in the ocean. Ocean currents are driven by the circulation of wind above the surface water, interacting with evaporation, sinking of water at high latitudes, and the Coriolis force generated by the Earth's rotation. So frictional stresses at the interface between the ocean and the wind causes the water to move in the direction of the wind. So large surface ocean currents are a response of the atmosphere and ocean to the flow of energy from the tropics to the polar regions. In some cases, currents are transient features and affect only a small area. Other ocean currents are essentially permanent and extend over large horizontal distances, and we'll focus on these permanent currents. On a global scale, large ocean currents are constrained by continental masses found bordering the 5 oceanic basins. Continental borders cause these currents to develop an almost closed circulatory pattern that are called subtropical gyres. Each ocean basin has a large gyre located at approximately 30 degrees north and 1 at 30 degrees south latitude in the subtropical region. These currents in these gyres are driven by the atmospheric flow produced by these subtropical high-pressure systems, which we'll discuss in detail in Chapter 5. In the southern hemisphere, roughly at 60 degrees south, these gyres systems don't develop because of the lack of the constraining landmass and form a circumpolar flow called the west wind drift, which is the only ocean current that is unbroken by any continent. So on either side of the equator, in all ocean basins, there are two west-flowing currents, the north and the south equatorial. These currents flow between 2 and 4 miles per day and usually extend 300 to 600 feet in depth below the ocean surface. The equatorial countercurrent, which flows towards the east, is partial return of water carried westward from the north and south equatorial current. In El Nino years, this equatorial current intensifies in the Pacific Ocean. Flowing from the equator to high latitudes are the western bound currents, and these warm currents have specific names associated with their locations: the Atlantic Gulf Stream, North Pacific Kuroshio, South Atlantic Brazil, South Pacific East Asia, and the Indian Ocean Agulhas. All these currents are generally narrow, jet-like flows that travel at speeds between 25 and 75 miles per day. Western boundary currents are the deepest ocean surface flows, and they usually extend 3,000 feet below the ocean surface. Flowing from the high latitudes to the equator are the eastern boundary currents, and these cold water currents also have specific names associated with their location: the North Atlantic Canary, North Pacific California, South Pacific Benguela, South Pacific Peru, and Indian Ocean South Australia. All these currents are generally broad, shallow-moving flows that travel at speeds between 5 and 15 miles per day. In the northern hemisphere, these east-flowing Pacific currents and North Atlantic drift move the waters of the west boundary currents to the starting point of the east boundary currents. The South Pacific Current, the South Indian Current, and the South Atlantic Current provide the same function as the South Pacific. These currents are associated with the Antarctic Circumpolar West Current, which is the west wind drift. Because of the absence of land masses in this latitudinal zone, the Antarctic Circumpolar flows in continuous fashion, as I said, around the Antarctic and only provides a partial return of water to these three southern hemispheric ocean basins. While I just mentioned many different currents and drifts by name, I don't expect you to know these for the exam. However, you should know the following: the North Equatorial Current, Equatorial Countercurrent, South Equatorial Current, and the West Wind Drift. So that concludes this lecture on Chapter 4. The remaining slides are the self-assessed quizzes that you can go at your own pace. As I mentioned, just right-click on the PowerPoint slide and select Pause, and this will pause the slide, and then again right-click on the slide and select Resume, and that will carry on with the PowerPoints. Till next lecture, have a good day.